Technology, Minna. I'm actually a visiting scholar at the Center for International Studies, and I'm on the fellowship of ETT. So my talk today is titled Beyond the Limits, using continuation power flow to predict and prevent grid collapses. Now, in my presentation, I will start by a brief description of the modern power grid and how the traditional neutral absent algorithm has actually failed us. And then the continuation power flow came into our rescue. And then in the context of my research, I will discuss how we use continuation power flow and present some results. And through the end, I also want to talk a little about the power supply scenario in Nigeria, particularly how that is shaping my research outlook in the next 5 years, and then also introduce the intra-African mobility funding that we are currently working on. So let's start. The modern power grid has been characterized with increasing load, and this is evident in the global market reports for consumer electronics that has been steadily increasing in billions of US dollars. And coupled with this, the need to decarbonize the power supply value chain, the modern power grid has also seen increased penetration of distributed generators in form of solar or wind. And this particularly has resulted in the modern power grid being operated very close to its limits. And this, of course, has resulted into some instability, particularly for networks of developing economies. And then we will see some examples, although 2 decades old, but not too far, of the widespread blackout of the North American system that was initially caused by weather situations, which result into high demand for air conditioning, which is simply load. And that resulted into one of the power lines being sagged and touching a tree. And then because of that, there are auto situations that the load on that line needed to be moved or transferred to other lines. And those lines also become congested, they sag, and then touching trees. And then it was a chain of cascading situations. And of course, that resulted into a blackout affecting over 50 million Americans in 2003. Again, this grid closer to their limit has also been manifested in the Nigerian power grid. Particularly, the statistics are actually not good because averagely, there are about 28 system collapses in Nigeria, averagely annually. And of course, within the last 22, 23 years, about 500 plus.
Is that like the total system or like one part of the system?
Well, total system.
Total system.
It's total system.
Like there's a blackout.
There's a blackout throughout the entire country.
Wow.
Yeah, so that's why I said the statistics are actually not really, they are better imagined. And this is caused majorly by power imbalance. There are a lot of loads and little generation. So it means that we needed some tools that will be used to predict and prevent these situations, right? And then we have traditionally the Newton-Raphson algorithm that tries to linearize the power flow equation using the Taylor series expansion, right? And then solve that for a single operating point. And this Newton-Raphson algorithm has actually worked fine, particularly when the network is far from its limit. However, for ill-conditioned networks, which is what we see in the modern power grid, particularly being stressed due to high load, the Newton-Raphson actually fails, particularly the Jacobian matrix become singular, resulting in instability, right? But this is precisely the point of interest for us, where the modern power grid is seen with increased load, with increased penetration of renewable energy. So the continuation algorithm actually came to the rescue. It does this starting by reformulating the power flow equation through a loading parameter lambda, and then it tries to solve this through the predictor corrector method, and then avoid the singularity issues that are associated with the Newton algorithms. And then compared to the Newton algorithm that tries to trace or find a solution within a map, that is find the solution of a single operating point, the Newton algorithm actually traces the entire map. And so what it does is to use predictor corrector method up to the points of bifurcation, which can either be the limit induced or even the saddle nose bifurcation. So yes, the continuation algorithm came to our rescue, but we needed the continuation algorithm to be able to respect some limits. For instance, the line flow limit, be able to also get us solutions that are within allowable voltage limit, and of course, remain stable. And this interestingly forms.
So is this like the continuation power flow? Is that the concept that's been around for a long time?
Yeah, the continuation power flow actually uses the continuation method in numerical analysis and adapted in the continuation power flow. So what this actually means is that we're running the Newton-Raphsons in a modified way, by using the continuation method in numerical analysis. So interestingly, those items, those constraints that we have identified, the thermal limits, the voltage and stability, interestingly form the limitations to power transfer, right? So when you're transferring power from one point to another, based on the conventional, very known power transfer equation, the power transfer is actually a function of first the sending and the receiving end voltages. Of course, also the characteristics of the line, which is measured in X, and then the angle between the voltages at sending and receiving end, which we translate into the stability rate. So I developed this limitation, which are new features in the MATPOWER continuation power flow algorithm, to be able to dictate the thermal limit, which translates to the transmission line or the cable coming characteristics, as well as the voltage constraint. And we contributed that to MATPOWER, which is an open source software. And that actually has earned us a mention in the MATPOWER development, particularly in documentation. So in terms of the transfer capability, we can see that the three constraints actually can happen at any point in time, depending on the loading condition of the network and all of that. So an important outcome of the continuation power flow algorithm is actually the PV curve. And the PV curve, just like I mentioned earlier, the continuation algorithm is able to trace the entire solution path of the power flow problem rather than just a single point in the map, in the solution space. So the PV curve actually is able to pinpoint the points of voltage collapse, or what we call the maximum or critical point. And then it's also able to distinguish clearly between the stable region and the unstable region. And of course, we always want to operate the network at the stable region. So when we zoom in again in the stable region, we're able to see that the continuation algorithm gives us the opportunity to know the voltage stability limit, which is actually the point of normal operating and the maximum voltage collapse point. And that difference actually gives us the stability limit. So this means that the distance from the nose point to the normal operating point is actually the point we should operate the power system in, and then the continuation algorithm is able to tell us this. So yeah.
How is that different from the Newton-Raphson algorithm?
Okay, the Newton-Raphson algorithm will not be able to obtain this point, because when approaching this point, the Jacobian actually becomes singular, which is not solvable, right? But the continuation algorithm is able to do that with the predictor corrector method and pinpoint particularly that this point is actually the voltage collapse point. Yeah, so good question. Thank you.
So does that point, you have to recalculate that point continuously, or does it remain?
Yeah, so the continuous algorithm, depending on the step size, does this by itself. and is able to identify that at this point, any of the three constraints or limitations that I mentioned can happen.
Yeah.
So depending on the loading and other system conditions.
Yeah.
So it's able to identify if it is a voltage point, if it is a line, or even if it is a stability limit point. You have questions?
How hard it is to estimate? I mean, question in the chat. Like how computationally, how difficult it is to estimate or calculate that point?
Yeah, it's not really difficult. It has been implemented in MATPOWER. All you needed to do is to run MATPOWER with these specifications. And this is one of the work I did for MATPOWER together with Ray Zimmerman of Cornell University to be able to say, okay, I'm running this continuation power flow, but I want the continuation power flow to be able to respect or dictate the three constraints, right? So and just with one line of code, you ask it to run and then it gets there. And apart from getting there, it also reports back to you that this is actually the cause of the maximum point, whether it is voltage, whether it is power limit, or even the generator reactive power limit that we have translated into the stability limit. So,
but there is no guarantee that this is in the feasible space, right? Or is there any guarantee?
yeah, there are lots of guarantee that this is visible.
Okay.
Yeah, this is visible. Thank you. Great question. Huh? Okay, so in the context of my research, how we deploy the continuation power flow, first, the problem we saw in the literature is that in modern power grid planning, particularly distribution system operators, due to the prerogative of the unbundled deregulation, where each of the companies now stand on their own, particularly in the developing world. In planning modern power grids, the distribution system operators plan distributed generators in distribution network, assuming that the upstream, the transmission network is stable, and thereby ignoring voltage control operations that can often come from FACT controllers, right? And FACT controllers are actually flexible AC transmission systems. They are power electronic based converters, right? And then also in the other end of it, the transmission system operators, the TSO, try to deploy these FACT devices, assuming that the distribution network downstream are passive. However, with the increased penetration of distributed generators, active distribution networks have emerged, right? And so, therefore, the existing literature before our research shows that these two operators are actually doing their things separately. So our research proposition is actually to move from the separate to a coordinated planning approach. So we looked at the coordination of FACT devices and distributed generators in an integrated transmission and distribution network, right? So in our approach, we developed a two-level optimization approach where the inner optimization actually implemented a hybrid of rate power flow performance index and particle swarm optimization for FACT device planning. And in the outer optimization, we actually implemented the multi-objective variant of the particle swarm optimization. And our goal actually is there are three objectives that we want to enhance, right? We want to enhance the transfer capability, which we call the ATC, that is available transfer capability. And according to NEC, the North American Electricity Reliability Commission, that ATC is actually the transfer capability remaining above the already committed uses, right? And then we also want to reduce the power losses and see how we also improve the voltage deviations from the nominal values. So you can see we have three objectives, and one of them is on one front, which is maximization, and the two are in another front, which is actually minimization. That is the active power flow and voltage deviations. We're actually in the minimization front. Yes.
So what is the rationale behind modeling it as a bi-level? Because bi-level program is kind of like a simultaneous game, right? I mean, you have the leader and you have the follower. Why not model it as a sequential game? Like, because you have the transmission line making the decision and then the DSO distribution making the decision. So it seems that it is more suitable to model it as a sequential game rather than a simultaneous game.
Yeah, okay. So what we did actually is not maybe my use of bilevel. What we did actually is to look at the transmission level first, and then do the planning, and then the output of that is actually fed into the distribution network, right? Which is that. So actually, that's what we look
Okay,
at.
so it is not bilevel in the optimization sense. It's like a multi-step.
Yeah, it's multi-stage. It's multi-stage. Yeah, thank you very much. So, and we were interested in knowing the correlation between these three objectives, right? And from that, of course, we wanted to see the Pareto front by looking at any of the two objectives. Now, this is our implementation. We implemented in MATLAB and MATPOWER. MATLAB specifically for the optimization using the particle swap optimization or its multi-objective variant, and then MATPOWER because of the continuation power flow. So we ran MATPOWER continuation power flow to evaluate our possible solutions. And as I said, because we had the objectives in two different fronts, we simply negated the ATC, the transfer capability term, so that all of them will now be on the minimization front, right? And then we use the dominance concept to now archive the non-dominated solutions for our Pareto front.
Sorry, so so you're saying PSO, particle swarm optimization. So what exactly do you use that for?
What?
The PSO, the particle swarm optimization.
The particle swarm optimization we use at the inner optimization for fax placement. Then we use it together with
the transmission.
Yes, at the transmission level. So we use it together with a performance index. We use the real power flow performance index to reduce the search space such that we are able to reduce the location, the possible locations of fax, and then use the PSO to now size the fact.
That's a planning problem. You're trying to find the optimal location for fax devices.
Yes.
So okay, have you solved the exact like formulation of the first stage problem? Like instead of like meta-heuristic, like is it tractable to solve the first stage, or it is like non-linear, non-convex, or anything?
Yeah, it's actually non-linear and non-convex. It's a non-linear and non-convex problem, and that's why we went for the optimization.
And also it's multi-objective.
Yes, of course, it's multi-objective. So thank you. Great question. Huh?
But I mean, on that also, can you ensure feasibility with the particle swarm optimization? Are you sure that you stay within a feasible?
Yeah, so that is why we did a hybrid of the particle swarm optimization and the real power flow performance index. So what the real power flow performance index does for us first is to look at the entire search space, and based on the sensitivity of the real power flow, it computes its sensitivity with respect to change in fact control parameters. But the real power performance index now actually reduces the search space to the visible solution. That now enables the particle swarm to only deal with so it reduces the search space so that it will be only within the visible search space. Yeah, so thank you. Great question. Huh? Okay, so in order to test this whole thing, we also developed a synthetic integrated transmission and distribution network. And particularly, we use the Western System Coordinating Council 9-bus network, which here we call the IEE 9-bus, and then the IEE 16-nodes distribution network. So we build a synthetic network where we have the 9-bus as transmission network and the 16 nodes as distribution network. And then this is actually the network statistics, and this is actually a line diagram of how it looked like. So the question we asked first is, can distribution system operators plan their distributed generators ignoring fax control operation, or generally voltage control operations? And in order to answer this problem, or this question, we took the IEA 16-node distribution network and then tried to plan DGs. And of course, the IEE 16 nodes has 3 feeders, and we consider each of these feeders has slack bus. That's 3 cases, right? And then we also look at when you have a distributed slack bus, right? So we solve these 4 cases trying to plan DGs. And then we now model the Western System Coordinating Council's 9-bus network as a transmission section of the IEE 16 nodes, right? And then that is because in the planning that I mentioned earlier, distribution system operators just assume that the transmission network is stable, right? So we want to make sure that we have a real transmission network at the distribution source. So now, interestingly, when we solve this, that is planning DGs here at the distribution network, none of the result is similar to the 4 cases that we have looked at in 1. And so we went further in 3 to get the Thevenin's equivalent of the transmission network, looking from the point of common coupling between the transmission and distribution network. And then when we try to solve or plan DGs now in the distribution network with the Thevenin's equivalent, we now got similar results with 2. And that actually tells us something. Yes.
Sorry, I just didn't get that point. Why, if you went from the slack bus to a stable, to my understanding from what you're saying is like a distribution system connected to kind of a very stable transmission system between 1 and 2, why isn't that equivalent from jumping, like why isn't having a slack bus that is kind of modeling those stable conditions the same as having a stable transmission system?
Yeah, thank you very much for the question. Now, in 1, what we looked at in 1 is because the 16 nodes has 3 feeders, right? Each of these feeders can be the slack bus, right? So we try to solve or plan DGs with feeder 1 being slack bus, feeder 2 being slack bus, and feeder 3 being slack bus. We obtain those results. We also obtain the result where we have a distributed slack bus, right? So we obtain that result. Now, the point is, usually this planning assumes that the transmission network is stable. And of course, there are transient and instabilities that can happen. Right? So we now went to 2 to now model for that same distribution network a given transmission network. And that transmission network does not necessarily mean a stable transmission network.
Got it.
Right? Doesn't necessarily model that has 1 per unit.
Got
The
it.
voltage has 1 per unit. Of course, the point of common coupling, the voltage here can differ.
Got it.
Right? So it is expected that because they have assumed 1 per unit at any of that, and this can actually differ, we don't expect the same result. And truly, we didn't get the same result. But then we're looking for a way to be able to do that and get the same result with this. And that means that we needed to model the PV and the slack bus exactly as what is seen here. And that is where we looked at the Thevenin's equivalent, looking at the points of common coupling. Hope that answers the question.
That's very clear. Thank you.
Thank you. So our result actually shows that voltage control operations from the transmission network get propagated into the distribution network. And particularly that when you plan DGs at distribution network in isolation, right, you get suboptimal results because the voltage control operations can change at any point in time, right? And then we also went further to do some sensitivity analysis. And then our result also suggests that when you solve or when you plan DGs at distribution network, what you are actually coming at is different static operating conditions, which may not necessarily reflect what you wanted, but they are suboptimal results. Now, in the, yes.
So by DG, you mean like rooftop solars and, or?
It can be, we were not specific because this is steady state analysis. We just were looking at the injection of power from a particular point, which can be from a distributed generator, could be a large farm, right? Could be a large solar farm or even a wind farm that is injecting at a particular
But the injection is not controllable. It's not from thermal, it is not that you can, it's not a firm power, it is a renewable.
Yes, yes,
Okay.
yes. It's renewable. Okay, thank you. So in the context of my research, that is the facts and DG coordination, how did we use the coordination algorithm also? You remember we talked about the objectives being transfer capability, power loss reduction, and the voltage improvement. So we looked at different power transfer transactions that usually happens in a deregulated electricity market. It could be bilateral or multilateral transactions, right? So we ran continuation power flow and obtain this and run the optimization and also obtain the transfer capability and other objectives. So these are possible some of the transactions that we have looked at, where you have the sources and the sink and their types. So for instance, the first one that we had is where generator 1 and 3 are actually being the supply bit, and load bus 5 is actually the demand bit. And then we run a lot of these transactions. But very interestingly, what we were interested in is how this three-dimensional Pareto front looks like, right? So this is one of them. And then we looked at 3 different types of fax devices. We look at the TCSC, that is the Thyristor Control Series Compensator. We look at the SSSC, that is the Static Series Synchronous Compensator, and then the UPFC, that is the Unified Power Flow Controller, right? And then interestingly, we obtain the slices of the Pareto front, and most of the transactions that we implemented, the power transfer transactions that we implemented are very similar. And we saw that there is a linear region, right, in the Pareto front. And above this linear region, where transfer capability is maximum, the Pareto front slope actually becomes 0, because it's actually now stiffened down. It means the slope is getting 0. Therefore, it implies that there is a maximum point where transfer capability can be enhanced with a particular type of fact. Above that point, any investment in fax devices to improve transfer capability becomes inefficient, because it means that we are not actually getting an increase in transfer capability in proportion to the power loss. And we also looked at that of the ATC voltage deviation, and of course, this is actually expected. So we also, as I mentioned earlier, we also looked at that of the static synchronous series compensator, and we saw similar results, and that of the unified power flow controller. But again, very importantly, we realized that for different type of fax devices, the transfer capability actually differs. And we also saw that the UPFC has obtained the higher transfer capability compared to the other type of fax. And this is actually expected because the UPFC controller has 2 voltage source converters back to back, one connected at the shunt to a bus and the other connected in series with a line. So it is doing 2 things at the same time, able to control bus voltages and also redistribute line power flows, compared to other type of fax that have only one source converters.
So
Yes.
just want to make sure I understand the plot. So what does each individual marker? What does each individual marker mean? And what do you have different colors and shapes?
Okay. So let me thank you very much for that question.
Yeah.
Okay, let me start from here. Now, the blue stars actually represents the archives of non-dominated solutions, because we have 3 objectives. Each of these blue line or blue colors represent a unique solution in the search space. That is, they are no any other solution is better than them in terms of 1 or 2 objectives. That is, they have a comparative edge over some other solutions. And then the black cycles are actually solutions that, because we sent out some swamp, right? And those solutions are actually not good compared to those ones. So we keep an archive of what we call the non-dominated solutions, that they are better in one way or the other compared to others. So the black ones actually are not good compared to those ones. So that is for the TCSC and DG coordination. For the SSSC, it is the red ones that are non-dominated solutions. That is, they are good solutions that can be taken within the visible search space. And then for the UPFC, again, the black ones are not good because they are dominated. Yeah, thank you. Yeah, so again, in contingency analysis, we use the continuation power flow again to run contingency analysis, particularly the single line outage contingency. And we saw that the continuation power flow is able to predict the voltage limitation, particularly when we run the transaction where all the sources are supplying the supply bit and all the loads are actually the demand bit. And we saw that bus 5 in this case, because the operating voltage is between 0.9 and 1.1 per unit. So we saw that bus 5 is actually the limitation to this type of power transfer transaction. And again, in another power transfer transaction, you can see all the buses are actually within the voltage limit operating point. But when we looked further from the results, we saw that it's actually a thermal limit. That is, one of the lines have reached its limit. Yes.
What do you mean? I'm just not informed well on this, but like, what is the contingency you're modeling?
Okay, contingency is actually trying to simulate the possibility of a fault where one line is taken out of the network. So what happens, right? When you take one line, and then it's actually called N-1, it can be N-2. It just assumes that what is the resilience of your network if you lose one of your equipment. And then N-2 would be when you lose two of the equipment simultaneously.
Okay. So this is this for the plot here, is this showing like an average over all potential removals, or is it?
Okay, it's actually for a given removal.
Okay,
Just for one removal. We just demonstrated this for just one removal.
Okay.
You know, contingency analysis is actually very expensive to run, particularly for very large networks. So we demonstrated this for just one removal. And then this is also for another removal, showing that the limitations can be different, and the continuation algorithm is able to capture or dictate each of those three limitations. Thank you. Great question. Yeah. So the continuation algorithm, how is it able to predict or prevent collapses, right? Based on all that we have identified or talked about so far. Now we see that the continuation algorithm is able to obtain solutions or even ill-conditioned networks, right? That is, networks that are very stressed. And by so doing, it's able to predict voltage collapse points. And that means that it enables the viability of power supply and demand bits. That is usually the issue in the electricity market. I want to see if my bid has a possible supply, right? Again, it is the output from the continuation power flow is able to tell us the voltage stability margin by identifying the transfer capability constraint, the three of those constraints. The limit, that's the thermal limit, the voltage, and the stability limit. And how is it able to do the prevention? Because the entire nose curve, when you run the entire nose curve, you are able to distinctly distinguish between the stable operating condition and the unstable region. And we always want to operate within the stable region. And of course, with contingency analysis, we also saw that when we run different contingencies, we know what is happening, which means that if we had run the contingency analysis in 2003, the 2003 blackout may not have actually happened. And then lastly, we're also able to compute the transfer capability, which we roughly relate as the stability margin with the continuation algorithm. This is how it is able to do that.
You're saying that they didn't do this in the blackout in the US in 2000.
Of course, the contingency analysis was not thorough. If it were thorough, we were able to know that, okay, if this line goes out, at this load, we now know that there will be a chain of reactions, because this is what happens. When that line sat due to increased loading, right, the best thing is for your breakers through the relays to get this line out of the network. So, and that actually happens. The protective gear got this line out of the network, but then the loads connected to this line needs to be transferred to other lines. And that is actually, and that also happened. And those loads were actually transferred to other lines, right? But when they transferred them to other lines, those lines also became congested. So if we had run contingency analysis, we'll have seen that when this line goes out and this load transferred to other lines, there will be another contingency, right? And then it now became a chain of reaction cascading into themselves. Is that okay? Yeah.
So that's what you mean by when you say predicting, like the algorithm can predict the outcome. Because I think that's, I was not unclear what you meant by predicting, but you mean like once you make the response to the contingency, you know kind of how the balance will kind of shake out.
Sure.
Okay.
Sure. When you know what happens with the what happens when the contingency happens, you now know your remedial measures, right? You know the remedial measures. Yeah. Thank you. So I also promised to talk a little about the power supply scenario, and that is actually a request from Adam, right? Yeah. So the power supply scenario in Nigeria actually depicts a situation of about 13 megawatts of installed generation capacity, out of which we're only able to deliver 5,000 or 5 megawatts. 5 gigawatt, 5,000 megawatts. And this is to about 250 million people. That's very low, right? Very, very low. Now, the cause of this is actually not far from what we know, aging equipment and all of that. And that has resulted into the incessant collapses. And of course, it is coupled again with increased technical losses. Of course, that is understandable because of the aging equipment. And of course, there is limited access to electricity supply, particularly in rural areas and underserved areas. However, there is some opportunities, some good opportunities, particularly with renewable energy integration. There are a lot of potentials in solar and wind with high wind speed, particularly in the northern parts of Nigeria. So this means that we can adopt some decentralized models, particularly in microgrids and mini grid. And when we couple that with smart grids and digitalization, such as forecasting and then fault detection, we are in a roadmap to a better energy transition for Nigeria. And then when we look also into what was presented last week about energy storage, that is also a very good option for us. Now, this is actually shaping my research focus going forward in the next 5 years. Particularly, I want to look at, or I am currently looking at sustainable energy solution for energy access for sub-Saharan Africa. And this is one of the reasons why I'm doing this here, to do some collaborative and innovative work in renewable energy with the professors here at MIT, particularly because of the current funding cuts by the US government, right? So we look outward to get funding for the underserved communities, and then we are able to contribute to the Sustainable Development Goal, that's SDG 7, for energy access globally. And so we can do this through pilot project implementation and community-led energy solution. And through this, we're also able to do some capacity development, such as knowledge transfer in those particular areas. So I hope that within my stay here, we try to do some grant sorting, some applications, and all of that. Now, I have started in this direction, particularly with the Intra-African Mobility Program.
Just on the Nigerian outlook, so you said there is a good potential for both wind and solar. So
Yeah.
are investments happening?
Yes, some investments, there are quite good investment that happen in that area.
Mhm.
And we saw that, for instance, in research, where in 2019, we won the Royal Academy of Engineering grant in the UK, that is for clean energy. We call it AI for CE, Artificial Intelligence for Clean Energy Solutions. And then currently we are working on the EU funding, which is actually homegrown clean energy solution project. And there it is an intra-African mobility program between about 6 universities. And we are exchanging students. And these students will go to different universities to develop clean energy solutions.
Nice.
Yeah.
Although you said you had 13 gigawatts, so installed capacity, is that like conventional thermal capacity?
Yes, those are conventional thermal as well as hydro.
Hydro?
Yeah, those are the two ones. Yeah.
So does the government have like plans for for renewables?
Sure. We have a renewable roadmap already.
Uh-huh.
Yeah. So we're just looking for investments in those areas, and particularly we needed to do some research before the investments can come in, right?
What about load growth? I imagine that the load is growing fast.
Yes, it is. It is. The load is actually the reason of the incessant collapses that we're looking at, because there is much load, and then the generation is actually not improving, particularly in the grid, right? So this is actually, the load is actually growing. For instance, in my university, we used to have the vice chancellor, of course, the president reported sometimes that our energy bill, for instance, was around 20, 30 million naira. And all of a sudden, it jumped to about 60, 70 million. So that's a huge load growth, right?
Yeah.
And then we're trying as a university to be able to manage the load, yeah? So that's huge load growth. And then in the university also, we're looking at the possibility of getting a solar farm, because the land, we are sitting in approximately 10,000 square hectares of a land, right? So it's very vast. And that is all over Nigeria. We have a lot of land for farming and all of that. Yeah.
So a lot of space. So you mentioned like microgrids as one solution.
Yes.
There's also, you could in principle build out a transmission network and invest in, let's say, large scale solar farms or wind farms.
Yeah.
So, are you taking like one of those directions or working on along both trajectories?
Yeah, so far, again, now, good question, because in 2024, the government actually, 2023, the government actually signed the 2023 Electricity Act, which now allows states to be able to generate, transmit, and distribute electricity. And then the states are now forming their own regulatory commissions to now license different companies to do this. Now, back in the university, we also have this plan to be able to do this in our university scale, but then supply surrounding villages around the university. So this is another thing. Yes.
So kind of maybe connected to that question, I've heard in like in some kind of developing electricity markets, you have an issue with people tapping into the power supply. So, you're not an official customer, but you connect your power supply to a transmission, or to some sort of supply of electricity. And it seems like that would disrupt the ability to control. You wouldn't have as much control if you don't know it's there, or you that's an unapproved entry point. Is that happening? Or?
Yes, it's happening.
Okay.
Right? It's power theft. Just go straight to the point. It's power theft, right? However, there are solutions to it, and we are implementing them back up, right? And the solutions are energy meters, smart energy meters that are incorporated with 5G technology. And when anything happens, you get an alert remotely from anywhere, right? So the utility companies, the distribution companies are implementing these solutions real time, right? Before now, what we used to have, why that is predominant, was analog meters that you don't have remote access to know what is happening, But now with smart meters, 5G technology, anywhere you get to see what is happening. And even from a control room, you know what, and then you can also follow the load pattern to see how this is changing and predict whether these things are actually happening. But it used to be really an issue.
It seems like also the microgrid might be less susceptible to that sort of
Yes.
theft than
Yes.
a transmission line.
Yes. Because it's now going to be at community level. And then one of the things that the Rural Electrification Agency is doing back home is to support community level microgrids, right? We build community level microgrids and the community actually owns it. And that means that the community is also policing themselves about those tests. Is that okay? Yeah, so great question. Thank you. Yeah, so I was talking about the collaboration that I seek here with MIT professors in this sustainable energy transition. So as I was talking about the homegrown clean energy solution, we already are on this, and then you can check us up at this website, hce.footmina.edu.ng. The project is actually funded by the European Union. And we at FOOTMINA are actually the hub universities, but we also have 5 other universities around Africa. We exchange students, and then these students come to look at clean energy solutions for climate change adaptation. And currently, I have a PhD student working on integrated clean energy solutions for what we term as net zero agricultural farms. Our definition of net zero is for the farm to be able to generate and use what it needs, the energy it needs. In other words, we want to ensure zero or minimal.
Fine, what size your lighter? Correct.
Sorry.
All right.
So we want to minimize or have even zero import of energy outside the farm. And we're doing this, of course, the challenge is no single renewable energy is able to meet reliably the energy needs of an integrated farm. And what we mean by integrated farm is possibly having a poultry, a rice farm, which usually has a lot of water requirement for irrigation, and then you need pumping machines and all of that. Then we have cattle, and then the veg farm. And so the renewable energies that we intend to hybridize are solar, wind, and biomass. Biomass because the cattle and the poultry will be able to produce a lot of this, and then we do biogas plants to do this. And then our goal actually, as I mentioned earlier, is to achieve up to 90% of renewable fraction with less than 2% power loss probability. And as I said, I have currently a PhD student from Cameroon that is working on this.
What do you mean with hybrid in this context?
Yeah, hybrid in this context is we are combining these 3 sources, and then they are the ones that will provide the power supply, right? And we want, because during the night, for instance, the solar is not there,
Sure.
then we can have storage.
Yes, but you don't have storage in your.
Yeah, we have it somewhere in
yeah.
the objectives, energy storage. So it's one of them in the objectives.
Yeah.
And then because we needed an energy management system to be able to manage these sources with the storage. And then we intend to do some techno-economic evaluation to see how that actually works.
And you do the evaluations on a, let's say, a village level or
Yeah, we are doing it at a farm level.
farm level?
Yeah, we're looking at an integrated farm that has at least the poultry, the cattle, the rice, and the veg farm, right?
Is it a typical farm in
Yes,
Nigeria?
yes,
or-
we already have a model farm. It's called Mezobe Farm, just beside the university. It's a commercial farm just beside the university. So we're getting our data from that farm. Yeah. Yes.
So the smart energy management system, from what you're describing, it seems like some of these energy management systems are being implemented in places that weren't receiving reliable power before renewables were implemented. It seems like that's a very big shift and potentially really interesting because you know, if people are already scheduling their use for when power is available, that would have, like, people would have habits associated with kind of energy scheduling that people like in the United States don't have. So it seems like that would create a good synergy for renewables because of kind of the path dependence of kind of people's habits.
Yeah, that's true. I agree with that.
More responsive.
Yeah.
Yeah. Yeah. So it's true. Yes, you want to ask a question?
I was wondering if there was a question there.
Okay, any question on that? Okay. So I think we have come to the end of my talk. Yeah. So thank you.
Thank you.
Interested in taking questions if there are any from those online also.
Sure. Thank you very much, Dr. Sadiq. Online participants, please ask your question, unmute yourself and ask your question if there is any.
Raised hands.
So while they're asking a question, for the Nigerian context, is there any like big pathway to also add thermal power plants like the gas power plants as well? Or?
Yeah, we have some thermal power plants, and also the government, as I said earlier, have decentralized the whole system with the Electricity Act, where states now going into building their own thermal plants, right? And then those thermal plants are specifically for some regions, not necessarily for the entire national grid, which we have shown us